Three inventions won the Second World War. The first two, radar and the atomic bomb, everyone knows. The third one saved more lives than the bomb took, shot down V-1 flying bombs over London, and stopped kamikaze attacks in the Pacific. It was called the proximity fuse. It was British, and you've probably never heard of it. That's not some throwaway claim designed to grab your attention. In 1946, James Phinney Baxter the Third, president of Williams College and official historian of the Office of Scientific Research and Development, published a Pulitzer Prize-winning book called Scientists Against Time. And in it, he placed the proximity fuse right alongside radar and the atomic bomb as one of the three decisive scientific achievements of the war. Not penicillin, not the Jeep, not the Norden bombsight or the Spitfire or any of the other things we've built documentaries and myths around for 80 years. A tiny device crammed into the nose of an artillery shell. And General George Patton, a man not easily impressed by anything he couldn't drive or shoot, writing after the Battle of the Bulge in the winter of 1944, declared, "The new shell with the funny fuse is devastating. I think that when all armies get this shell, we would have to devise some new method of warfare." Patton didn't say that about radar. He didn't say it about penicillin, or the Jeep, or the Norden bombsight either. So what was this thing? And why don't you know about it? To answer the first question, you have to understand the problem it solved. And that problem was, frankly, embarrassing. Anti-aircraft fire in the early years of the war was almost useless. Not metaphorically, statistically. The numbers were brutal. Various wartime analyses put the figure at somewhere between 2,000 and 2,500 conventional shells to bring down a single aircraft. That's a hit rate of roughly 1.65%. For every 100 shells fired into the sky, 98 did absolutely nothing. Here's why. The standard method relied on mechanical time fuses, little clockwork timers physically set by the gun crew before each shell was loaded. The crew had to estimate the altitude of an incoming aircraft, calculate its speed and direction, predict where it would be several seconds into the future, and then set the timer so the shell would detonate at precisely that point in the sky. If any of those calculations were off, even slightly, the shell exploded harmlessly in empty air. And slightly meant almost nothing. An aircraft doing 300 miles per hour covers 440 feet every second. A time fuse set 1 second too long detonated 440 feet away from the target, well outside the lethal fragmentation radius. Against a diving attacker or a maneuvering pilot, the maths became essentially impossible. Anti-aircraft fire was, in the honest assessment of many gunnery officers, a form of organised prayer. The idea that would change everything came from Britain, specifically from a man named William Alfred Stewart Boutmont, an Australian-born physicist who'd been working at British military research establishments since the 1930s. Boutmont wasn't a desk theorist. He was an extraordinarily practical inventor. He'd already co-developed one of the earliest radar systems for coastal defence. In May 1940, with the Blitz looming, Boutmont submitted a formal proposal, together with Edward Shire and Ninnis, for something radically different: a radio frequency proximity fuse. The concept was elegant in principle. Instead of a clockwork timer, the shell would carry a miniature radio transmitter in its nose. That transmitter would broadcast a continuous signal as the shell flew. When the signal bounced off a nearby aircraft and returned to a receiver also inside the shell, the Doppler frequency shift caused by the closing distance would trigger a thyrotron switch and fire the detonator. The shell didn't need to hit the target, it just needed to get close. Boutmont's design became the foundational blueprint for what would be designated the VT fuse, VT standing for variable time, a name deliberately chosen to mislead anyone who heard it. Decades later, in 1965, the American firm Varian tried to claim prior invention. The claim was dismissed. Patent priority was granted to Boutmont and his co-workers. The legal record is unambiguous: British invention. And Boutmont wasn't working alone. As early as September 1939, the very month war broke out, the physicist John Cockcroft had begun a development effort at Pi Limited, the Cambridge wireless manufacturer, exploring whether radio valve technology could be miniaturized enough to survive being fired from a gun. During 1940 to 1942, Pi pursued this as a private venture initiative and produced critical practical insights. Samuel Curran and his wife Joan Curran, both formidable physicists, were transferred to the Telecommunications Research Establishment near Malvern, where they contributed to proximity fuse development alongside other classified work. Joan would later become famous for inventing window, those strips of aluminium foil dropped by bombers to confuse German radar. Her proximity fuse work remained classified and largely unrecognized for decades. A pattern you'll notice keeps repeating in this story. But Britain in 1940 had a problem no amount of genius could solve. It was fighting for its survival. It simply didn't have the industrial capacity to turn a laboratory concept into millions of mass-produced shells. For that, it needed America. The mechanism by which the proximity fuse crossed the Atlantic is one of those stories that sounds too cinematic to be true. In August and September of 1940, Sir Henry Tizard, rector of Imperial College London, led a small mission of British scientists to the United States, carrying a battered metal deed box. Inside that box was the entirety of Britain's most advanced military technology. Blueprints, technical documents, working prototypes. The centerpiece was the cavity magnetron, the device that made centimetric radar possible. Baxter later called it the most valuable cargo ever brought to our shores. But the magnetron wasn't alone. Among the other technologies in that box were Boutmont's designs and the practical insights from the Pi and TRE work on the proximity fuse. Britain handed America its secrets. All of them. In the middle of a war, it was losing. The Americans moved fast. Vannevar Bush, the engineer heading the National Defense Research Committee, recognized the fuse's potential immediately and assigned the project to something called Section T. Deliberately bland name. Section T was led by Merle Tuve, a physicist at the Carnegie Institution of Washington, who'd pioneered using radio pulses to measure the height of the ionosphere, work that had, ironically, helped lay the groundwork for radar itself. And this is where the story pivots, because Section T didn't stay at the Carnegie Institution. By early 1942, the project had outgrown everything. Every lab, every workshop, every makeshift testing space they could cobble together. The solution was the creation of an entirely new institution, the Johns Hopkins University Applied Physics Laboratory. APL wasn't repurposed from something else. It was built from scratch, specifically and exclusively to develop the proximity fuse. That's how important this program was. They created a whole university laboratory just to make it work. Tuve ran APL like a man possessed. He recruited physicists, engineers, chemists, glassblowers, machinists, anyone who could solve the cascading chain of problems that stood between a brilliant British concept and a device that actually worked when shot out of a cannon. The operation coordinated a manufacturing network that eventually spanned the American electronics industry. But first, they had to solve the problems. And the problems were, by any reasonable standard, absurd. What Tuve's team had to do was build a complete functioning radio station. A transmitter, a receiver, an amplifier, an electronic switching circuit, a power source, and a detonation trigger, and fit the entire assembly into the nose cone of a standard 5-inch artillery shell. The available space was roughly the volume of a fist. Then, that miniature radio station had to survive being fired from a gun. Think about the forces involved. When a 5-inch anti-aircraft shell is fired, it experiences a setback force of 20,000 G, 20,000 times the force of gravity. A fighter pilot blacks out at 9 G. An object weighing 1 ounce at rest effectively weighs over 1,000 pounds during that fraction of a second acceleration. Every vacuum tube, every wire, every solder joint, every capacitor, all of it had to endure that instantaneous, crushing violence and come out the other side not just intact, but working perfectly. The vacuum tubes were the hardest part, and the Johns Hopkins team went through an agonizing cycle of failure before they cracked it. Standard radio valves of the era were made of glass with delicate internal elements that would shatter instantly under 20,000 G. Early prototypes failed constantly. Tubes that worked perfectly on the bench disintegrated the moment they were fired. The filaments snapped. The glass cracked. The internal elements shifted fractions of a millimeter, which was enough to make them useless. Shell after shell came out of the test gun, dead on arrival. 20,000 G of force, followed by silence, where there should have been a radio signal. The breakthrough came from an unlikely direction. Companies like Raytheon and Sylvania, working under APL's coordination, drew on their experience with hearing aid valves, already the smallest commercial vacuum tubes in production, and re-engineered them for an environment those hearing aids could never have imagined. Reinforced filaments, carefully redesigned internal geometry that distributed G-forces instead of concentrating them at failure points. Then the tubes were potted, embedded in solid compounds, filling every gap, so nothing could vibrate or shift, not even slightly. Each new design went back into the test guns at APL's proving grounds, and slowly, agonizingly, the survival rate climbed. Eventually, reliable enough to bet lives on. These weren't elegant theoretical problems. They were ugly, practical, life-and-death engineering puzzles, and the people at APL solved them one by one through sheer, dogged repetition. The battery was its own small masterpiece of violent engineering, and it deserves to be pictured because it's brilliant. The fuse needed electrical power, but a conventional battery sitting in an ammunition magazine for months would slowly discharge and be dead when needed. So they designed a reserve battery, one that kept its chemical components separated until the moment of firing. The electrolyte was sealed in a glass ampule at the battery's center. When the gun fired and the shell began to spin, artillery shells rotate at enormous speed for stability, the centrifugal force shattered the ampule and drove the electrolyte outward into contact with the battery plates. Picture it. The instant the gun fires, the spinning shell crushes a tiny glass vial inside itself. Liquid floods outward through channels no wider than a pencil lead. A battery that was inert a heartbeat ago surges to full power. From dead storage to full electrical output in the time it took the shell to clear the barrel. This had to work every single time. In Arctic cold, in tropical heat, millions of times. And once powered up, the fuse did its actual job, broadcasting a radio signal from an antenna built into the nose cap, listening for the Doppler-shifted echo bouncing off a nearby target, and detonating the shell when the target was within roughly 70 feet. No direct hit required, no perfect calculation, no prayer, just physics. In the space of a fist, spinning at thousands of revolutions per minute, after surviving a force that would flatten a small car. A miniature radio station woke up, powered itself on, broadcast a signal, listened for its own echo, measured the frequency shift, and made a life-or-death decision. All in the seconds between the barrel and the sky. That it worked at all is remarkable. That it worked reliably, millions of times, is one of the great engineering achievements of the 20th century. And the place that made it work, the institution that turned a British concept on paper into a weapon that functioned in rain and snow and tropical heat, that survived 20,000 G and armed itself in mid-flight, was Johns Hopkins APL. Full stop. The first combat use came on January 5, 1943. The light cruiser USS Helena, operating near Guadalcanal, fired proximity-fused 5-inch shells at incoming Japanese aircraft. The results were immediate. Aircraft that previously required thousands of rounds were being destroyed with dramatically fewer shells. The Navy was convinced. Production ramped through 1943 and 1944, with Johns Hopkins APL coordinating a manufacturing network spanning the American electronics industry. By the war's end, more than 22 million proximity fuses had been produced, each one essentially a bespoke electronic device requiring precision assembly of miniature components, each one a tiny radio station built to survive the unsurvivable. This is the honest framing the story demands. Britain conceived the impossible idea. Johns Hopkins made it real. American industry built it at scale. Nobody could have done it alone. But, and this is critical, there was a strict, almost paranoid condition on its use. Naval combat only. The logic was coldly rational. A proximity fuse that worked properly detonated near its target and was destroyed. But duds, shells that malfunctioned, would fall to earth intact. Over the ocean, a dud shell sank and was gone. Over land, a dud could be recovered by the enemy, reverse-engineered, and turned against Allied bomber formations. If the Germans fitted proximity fuses to their Flak 80s, the strategic bombing campaign might become impossible. Thousands of bomber crews would die. For this reason, the proximity fuse was classified at a security level that, according to multiple wartime accounts, exceeded even the Manhattan Project. The atomic bomb was the most secret weapon program in the world. The proximity fuse was more secret still. This wasn't bureaucratic overcaution. It reflected a hard military calculation that losing the fuse's secret could immediately cost thousands of aircrew lives over occupied Europe, while the atomic bomb's secret, though enormously important, didn't face the same risk of rapid enemy exploitation in an active theatre. The most secret weapon of the war, and you'd never heard of it. The naval-only restriction held until two crises forced the secret into the open. The first came on June 13, 1944, 1 week after D-Day, when Germany began launching V-1 flying bombs at London. The V-1 was crude but terrifying. A pilotless aircraft powered by a pulse jet engine carrying an 1,870-pound warhead screaming in at 400 miles per hour at altitudes between 2,000 and 3,000 feet. Over the course of the campaign, 9,500 V-1s were launched against England. The defence, codenamed Operation Diver, was layered. Fighters, a balloon barrage, and a belt of anti-aircraft guns. But the guns, still firing with conventional time fuses, were achieving dismal results. The V-1 flew fast and low, giving gunners almost no time to calculate firing solutions. Time fuses had to be nearly perfect against a small, fast target. And nearly perfect wasn't something time fuses did. V-1s were getting through in devastating numbers. By mid-July 1944, thousands of Londoners had been killed. By the campaign's end, 6,184 civilians were dead, each one a person who happened to be standing in the wrong place when a pilotless bomb they never saw dropped out of the sky. So the decision was made: deploy proximity-fused shells to the gunbelt. Over land. British land. The gunbelt was reorganised and redeployed to the coast of southern England, positioned so that shells that missed would fall into the sea rather than onto English soil. The transformation was almost instantaneous. Before the proximity fuse, the gunbelt was destroying roughly 24% of V1s entering its zone. After the introduction of proximity-fused shells, combined with SCR 584 radar for automated gunlaying, the kill rate soared. By the last week of August 1944, the guns were destroying 79% of all V1s that entered their engagement zone. And then came the day that proved it beyond all argument. On August 28, 1944, 97 V1 flying bombs approached England. 4 got through. 4. 93 were stopped. The transformation had taken weeks, not months. A weapon that was slaughtering Londoners by the thousands was neutralised by a device the size of a fist. A device conceived in Britain, engineered at Johns Hopkins, and now saving British lives over British soil. There's a symmetry there that almost feels designed. In the Pacific, the proximity fuse faced a different kind of horror. Beginning in October 1944, at the Battle of Leyte Gulf, Japan unleashed kamikaze attacks against the Allied fleet. Aircraft deliberately crashed into warships by pilots who had no intention of returning. A kamikaze didn't need to score a precise hit. It just needed to reach the ship. And conventional anti-aircraft fire, even when it struck the aircraft, often couldn't destroy it completely before momentum carried the burning wreckage into the hull. The mathematics of kamikaze defense were terrifying. An aircraft diving at a ship from altitude closed at tremendous speed. Gun crews had seconds. With conventional time fuses, those seconds were mostly wasted. Shells bursting too high, too low, too far behind. The aircraft kept coming. Proximity-fused shells changed the equation. They didn't need a direct hit. They needed 70 feet. And at Okinawa, from April to June 1945, this mattered more than anywhere else in the war. The Japanese launched over 1,900 kamikaze sorties against the Allied fleet off Okinawa. Ships were hit. Ships were sunk. Even with proximity fuses, the kamikaze campaign killed roughly 4,900 American sailors and wounded 4,800 more. Those numbers are staggering. But here's the thing. Without effective proximity-fused anti-aircraft fire, the losses in ships and men would have been catastrophically greater. Every kamikaze that detonated 70 feet from a ship instead of impacting the deck was a crew that survived, a vessel that stayed afloat, sailors who went home after the war to lives they almost didn't get to live. The fuse couldn't stop every attack. Nothing could. But it turned kamikaze strikes from a near-certain hit into something survivable. And across hundreds of engagements, that difference added up to thousands of lives. And then there was the Ardennes, December 1944, the Battle of the Bulge, Germany's last major offensive in the West. A surprise attack through the frozen forests of Belgium and Luxembourg that caught the Allies completely off guard. American units were surrounded, overwhelmed, in some places overrun. The situation was desperate enough that the military crossed the last remaining line, authorizing the proximity fuse against ground targets for the first time. The shells arrived at the front lines in the dead of winter. When they were fired against massed German infantry formations advancing across open ground, the effect was devastating in a way ground troops hadn't seen before. A conventional artillery shell with a contact fuse hit the ground and exploded upward, and soldiers in foxholes or behind cover had reasonable protection. A proximity-fused shell detonated in the air, 20 or 30 feet above the ground, showering shrapnel downward across a wide area. There was no hiding from it, no foxhole deep enough, no tree thick enough. German soldiers, caught in the open under airburst fire, experienced a weapon they had no answer to and no understanding of. The shells seemed to detonate at exactly the worst possible height, every single time, without fail. That's what Patton was talking about. The new shell with the funny fuse. Funny. The man had a gift for understatement. So add it up. Lives saved from V1 intercepts over London. 6,184 civilians died, but without the fuse, with only that 24% intercept rate instead of 79%, thousands more would have followed. Lives saved from kamikaze defense across the Pacific. 4,900 sailors killed, even with the fuse, catastrophically more without it. Lives saved in the Ardennes, where the war's momentum shifted partly on the strength of shells that burst in mid-air. Hiroshima and Nagasaki killed between 110,000 and 210,000 people, depending on the source and time frame. The cumulative lives saved by the proximity fuse across every theatre, across every engagement from January 1943 to August 1945 is defensibly larger than that number, probably much larger. Which brings us to the real question. Why don't you know this? Partly because the fuse's wartime secrecy meant no propaganda, no newspaper headlines, no heroic narratives built around it while the war was still being fought. Radar had visible infrastructure, towers, dishes, installations people could see and photograph. The atomic bomb had Hiroshima, a single, searing image that defined the 20th century. The proximity fuse had nothing visible at all. It was literally invisible. Hidden inside the nose of a shell that either exploded or sank to the bottom of the ocean. No dramatic single moment, no mushroom cloud, just a steady, quiet accumulation of lives not lost, ships not sunk, bombs not arrived. And Britain's role was obscured by the sheer scale of American production. 22 million fuses, built in American factories, deployed by American forces. The name everyone remembered, if they remembered anything, was Johns Hopkins. Not Boutmont, not Cockcroft, not Pye Limited in Cambridge. Easy to forget who had the idea in the first place. Easy to forget a physicist who filed a proposal in May 1940 and whose patent priority wasn't even upheld until 1965, 20 years after the war ended. Radar is in every history book. The atomic bomb defined a century. The proximity fuse, the one that saved lives instead of taking them, is the one nobody remembers. Britain's greatest contribution to winning the Second World War wasn't just helping build the bomb. It wasn't just inventing radar. It was a tiny radio transmitter inside an artillery shell that turned a 1.65% chance into near certainty, that turned V1s hitting London into V1s falling short, that turned kamikazes sinking ships into kamikazes blown out of the sky before they could reach the deck. Conceived in Britain, engineered at Johns Hopkins, classified above the atomic bomb, used 22 million times, and almost completely forgotten. Now you know. Tell someone. And if you want more stories like this, the ones history somehow forgot, subscribe.